probably been a while since you've looked at logarithms. So just to kind of quickly review how we analyze them, how we evaluate them, we just have to start off by realizing that exponents and logarithms are essentially derived from one another. So the properties of each can essentially, in one way, shape, or form, be used to help evaluate the other. So just the most basic reminder would be converting between logarithmic and exponential form. So if you're given an example such as 5 to the x equals 25, you're essentially saying 5 is what we call the base. You're saying, what do I raise this base to in order to wind up with 25? The logarithmic form, it's essentially expressed in the same way, except the log with the small number gives you the base. So this is log base 5, and it's just saying 5 raised to what power will give you 25, essentially. So it's two different ways to say the same thing. You're probably most used to the exponential form. Just realize 5 to what power equals 25 is how you'd read the exponential form. And the way to read the log form would be, well, 5 to the what power will give you 25. All right, so it's just a different way of restructuring this, and that provides some advantages and at times disadvantages depending on what you're trying to find. So just to look at a few more examples, just to make sure you're clear. 4 to the third equals 64. Well, this base of 4 raised to the third will give me 64. So in log form, log base 4, 4 to the third gives me 64. X to the fifth gives me 73. So x to the fifth gives me 73. 7 to the y gives me 98. 7 to the y gives me 98. So the exponent in log form is essentially all by itself, and then the base is just put next to the log, and then your final result is what you include within the parentheses of the log. When we're looking at the properties of logs, you're going to have to have access to the four major rules: the product rule, quotient rule, power rule, and equality rule, or properties, whatever you'd like to call them. And I'm not going to review all of them in great detail, but you can see through them that if you have a log of some base and there's two numbers that are being multiplied, well, that's the same as adding both of those with the same base. So log b of m times n is the same as log base b of m plus log base b of n. Quotient rule is just the opposite. If you have a log and you're dividing two numbers inside of that log, well, you can just subtract those two. The power rule states that if you have an exponent on your value inside the log, you can move that to the outside and it can become a constant. And the equality, if you have the log of base b of some number equals the log of the same base of another number, then those two numbers have to equal one another. So if you use this just kind of as a general guide, it tends to help as you work through these problems. So just to show you a few quick examples, hopefully jog your memory. If you were given a problem such as the log base 7 of x equals the log base 7 of 35, well, both of these bases are the same, so that tells you that the equality rule is applicable. So if two logs of the same base, in this case log base bm equals log base bn, then m and n must be equal to one another. So in this case, if the log base 7 of x equals the log base 7 of 35, well, x must equal 35. Sometimes you'll combine these rules. So log base x of 15 plus log base x of 3 equals log base x of y. Seems a little bit more complicated, but we can immediately realize here that this is the product rule. If I'm adding two logs of the same base, go away. If I'm adding two logs of the same base, well, that also means that I can simply take the log and multiply those values together. So if we take a look, log base x of 15 plus log base x of 3, well, that's the same as saying the log base x of 45, because I can take the 15 and the 3 and I can put them together with a log of the same base. So this now becomes log base x of 45 equals log base x of y, based on the product rule. And then hopefully, from a previous example, you can see anytime I have two logs of the same base that are equal to one another, well, based on the equality rule, as I showed previously, those values inside must be equal to one another. So the equality rule therefore tells me that 45 equals y. So this is hopefully starting to jog your memory. You just have to realize, use these rules, and they'll help you figure out what's going on. Another quick example, log base 8x to the third equals 6. Well, hopefully the power rule stands out here because you are being raised to a power here. So the power rule tells me that log base b of some value raised to, in this case, p, well, I can take that exponent, I can make it a constant on the outside. So I can take that 3, make it a constant, and then I can just solve this as I normally would. Divide both sides by 3, and then I can just convert that back into exponential form. Remember, 8 to the second will give me what? So 8 to the second gives me what? And therefore x must be 64. So you're just using the variety of these rules to basically reorganize these equations and try and find a more efficient way of solving these. The only other types of logs you need to look at would be the common and a natural log, and these are things you probably remember. The common log is just a log that has a base of 10. You won't always be given a log and a base. Anytime you're just given the word log, it's assumed that the base is 10, and that's a common logarithm. Common and natural logarithms are really, really good because they allow you to use your calculator. Not all calculators can do log of custom bases. Most of them can only do the log of base 10 or a natural log. Natural log is just based on e, and if you remember back, e is roughly negative 2.72, something like that. There's a whole bunch of decimals afterwards. Natural log is written as ln, and I left it out here on accident, but anytime you see ln, it just means log base of e, so this should say log. And the last tool you might need would be the change of base formula. And you essentially, if you're given a log of a certain base of a value, if you'd like to convert it to another base, you do so as such. You take the log of whatever base you'd like to convert it to, n, divided by the log of whatever base you'd like to convert it to, a. Now it seems weird because a lot of times you could just plug either side into your equation, to your calculator, but to show you the example here, if you're given the log base 5 of 17, you likely won't be able to solve that in your calculator because your calculator probably can't do log base of 5. I know in this case, with the numbers I gave, you could certainly arrange it into exponential form, but let's ignore that for a second. If I wanted to convert this to log base 10, well, that would be a pretty good base to convert it to because log base 10 is something my calculator can do. So if I take this, log base 10, I'd like to convert it to base 10. N in this case is 17, so 17 goes on top. A in this case is base 5, so it goes in the bottom. This is not something I could plug into my calculator, most likely. This is something that I could, because log base 10 is something my calculator can do. If I plug that in, I will find that this comes out to about 1.76. I can take the same problem, and instead of converting it to the common log, I could also convert it to the natural log, which my calculator can then do. And I'll find that the answer is also 1.76, obviously. This is more of a powerful tool when you're trying to analyze some kind of log and your calculator has limited capabilities. They won't always be this easy. You could obviously solve this one several other ways. But in cases where maybe one of these is an unknown variable or something like that, converting to a base that your calculator can analyze will allow you to solve those problems.